Assalamu alaikum. This is the demonstration of video for the 6-bit SAP1 computer as part of the EEE 4308 course. I am Baksh Mohammad Mahanna, presenting on behalf of Team Asynchronous Error. The term SAP1 means simple as possible. Our 6-bit SAP1 will be able to perform arithmetic operations such as addition and subtraction for 6-bit binary numbers. First, I will be explaining the different components of the computer as well as its overall architecture. Then we'll test it out and demonstrate how it works. Let us now go over the components one by one. At first, we have the clock. The clock pulse signal is what controls the operation of the computer. It has two modes of operation, auto and manual. This is the child sheet. Here, as we can see, this clock is being operated by a 555 timer IC. So next, we have the program counter. The job of the program counter is to store and send out the memory address of the next instruction to be fetched. It is essentially an up counter that can count from 0 to 9. In binary, that is from 000 to 111. However, the counter has been designed in such a way that when the input at CE pin is set at 1, only then will it increment, and so that means it will only increment its value after every instruction cycle. So at the first instruction cycle, the output will be 000. Then at the next instruction cycle, the output will be 001, and so on. Next, we have the memory address register, or MAR for short. This is essentially a 3-bit register. It stores the 3-bit address of data or instruction which are in RAM. Here, right next to the MAR, we have the address selector. This address selector is needed because when the SAP is being programmed, the address fed into the RAM must be coming from the input unit. However, when the computer is operating, when it is in run mode, at that time, the address fed into the RAM, it needs to be coming from the MAR. So the selector is nothing more than a mux IC, as you can see when we go to the child sheet. This is nothing more than a single multiplexer IC. So it takes input from both the MAR and the input unit, and depending on whether we set it at program or run mode, it will either pass the input from the MAR or from the input unit to the address field of the RAM. Next, we have a very vital component of our RAM, of our computer, which is the RAM. So here we have used an 8 into 6-bit RAM. Let's go to the child sheet. So here we have used an 8 into 6-bit RAM, which means it will have 8 addresses, and each address can store 6 bits. So each word that is saved into the RAM is 6 bits. The RAM can be programmed by these address switches over here. So the micro instructions will be saved in the RAM. So the micro instructions are 6-bit, and those 6 bits for each micro instruction will be saved to their corresponding addresses. So every address will contain a micro instruction. That is essentially how we code this computer. So the code will be saved in the RAM and will be fetched from the RAM according to the instructions given by the controller sequencer, which we will see soon. Now we have the ALU, or arithmetic logic unit. This ALU is just an adder subtractor. So essentially when SU is set at 1, it will subtract, and when EO is set at 1, it will add. So the inputs at ALU are coming from the accumulator and the B register. So when EO is set at 1, the inputs coming from the accumulator and the inputs coming from the B register will be added, and here we will get the output and the output terminal. And when SU is set at 1, so when the ALU is subtracting, it will subtract the input that it gets from the B registers from the input that it gets from the accumulator. So it will perform subtraction between A and B. So the the higher number with higher value will be on top, it will be saved in the accumulator, and the number with lower value will be saved in the B register. So that's how it will subtract from the number at the top to the number at the bottom. Connected to the ALU, we have the three registers. So we have accumulator, B register, and output register. So essentially, these are storage units. So the accumulator and B register stores 6-bit data as input to the ALU, while the output register stores the result to the display when needed. As we can see here, the output terminals of the ALU are connected to the output register. So this output register will store the output of the ALU and display when we request it. So here, as you can see, the BI pin coming from the controller, this is what decides when the output register displays our outputs, the OI pin. Now let us have a look at the brain of this computer, which is the controller sequencer. The controller sequencer generates necessary control signals for each block so that actions occur in a desired sequence. 12 control bits come out of the controller sequencer block. These control bits determine how all the other blocks will react to the next positive clock edge. So here, if we get 1 at the output, then that means the corresponding blocks will be active, and for 0, they will be inactive. The controller is designed in such a way that the correct control bits are already available to all the blocks before the next positive clock edge. Besides these 12 signals, controller sequencer also sends a halt signal, as we can see here. So when this halt signal is sent, as we can see, this halt pin is connected directly to the input of the clock. So when this halt signal is sent, the clock will stop immediately. So after that, the clock will no longer pulse and the operation of the computer will be stopped as well. It will only resume once we have reset the entire machine. So only then can we perform a new operation. Now the instruction register. The function of the instruction register is to receive and store the 6-bit instruction placed on the bus from the RAM. So the contents of the instruction register are then split into 3 upper bit segments and 3 lower bits. So 2 segments, that is, 3 upper bits and 3 lower bits. So the upper bits are sent to the controller sequencer and the lower bits are sent directly to the bus. A reset pin is also used to reset the instruction register. So the reset pin will be useful when we are trying to start a new operation. So before starting a new operation, we will reset several components together. So we will reset the controller sequencer, we will reset the RAM and several other components. All reset pins are shorted together to one reset button, the reset button that we can see here. Now I will be demonstrating the operation of the SAP computer. Let us add two numbers, say 21 plus 15. So we will be adding 21 and 15. Now first, let me show the code for this operation. So here we have the code for this operation. This is the code for this operation. As I demonstrate the process every step by step, so at that time I will be explaining these codes, these lines of codes one by one. So let us begin the process. At first I will load this data into the RAM. So these are the addresses and these are the instructions. So at these addresses we will save their corresponding instructions. So let us save the instructions one by one. So as we can see, at 000 address, the corresponding instruction will be 000101. So at the top, we have the most significant bits and we have the least significant bits at the bottom. So let us start. First, let us turn on the simulation. Now at the address 000, we will save 000 101. So 000 101. So now we'll have to pulse this save button once to actually save the data to the corresponding address. So here we have pulsed this save button, and now this data is saved at the corresponding address. So let us continue doing this. Now at 101, we will save the first number, that is 21. So we will save the binary of 21. So the binary of 21 is 010101, saved. And at 110 address, we will save the binary of 15. So the binary of 15 is 001111, saved. Now we have saved the instructions to their corresponding addresses. So now we will run the computer. So let us set the RAM to read mode and the address selector to run mode. Now first let us set the clock at auto pulse. So here, as we can see, the operations are going on. Here we have the output. So 21 plus 15 equals 36, which is the correct output. So now let's explain the T states one by one. So first, let's stop the auto pulsating and reset the machine. Now we will pulsate the clock manually. First, our SAP computer has 5 T states. So for every instruction, there are 5 micro instructions. So let us begin. So at the first clock pulse, as we can see, the CO and MI pins are activated. So that means the output from the program counter, which is, as we can see, 000 at the moment, will be sent to the MAR. And as we can see, the output 000 is saved at the MAR. So this happens at the state T1. So there are 5 states: T1, T2, T3, T4, T5, and at T1 this is what happens. This is for the first micro instruction. So this first line 000 101. So now we have sent 000 at the counter at the mark. So let us pause it again. So as we can see, now the the instruction that is stored at 000, which is 000101, we can see this instruction is visible at the bus. Now here we can see our first line of instruction is fetched on the bus. The 000 stands for LDA, which means load accumulator. So this is the load accumulator operation, and the 101 is the address at which the first number is stored. So the data at 101 will be loaded into the accumulator. So here, as we can see in this state, CO, RO, and RI pins are activated. So this means here the output from the MAR, which is at this moment 000, is being sent to the RAM's address field. So here at this address field, we are getting 000. So the output of the data saved in this address, which is 000101, this is being sent to the bus, and now the instruction register is taking that data in, and it is dissecting that data. This was the second T state, T2. And now we have T3, the third state. Now, as we can see, the bits MI and IO have been activated. So the instruction register now gives its output. So in the previous T state, the instruction register took the 6-bit data from the bus and it dissected that data. Now it is outputting the dissected data. So the upper 3 bits, they are being sent to the controller sequencer. So the micro instruction 000 is being sent. So 000 stands for LDA, as we know. So the micro instruction LDA, load accumulator, is being sent to the controller sequencer. And the lower 3 bits are sent to the bus. These 3 bits are the address, the data from which will be sent to the accumulator, will be loaded to the accumulator. So this is the address of that data, the address of our first binary number, 21. Now let us pulse the clock again. As we can see, now we are at T4 state. The RO and II bits are active, as we will see. RO and AI bits are active. So now the data saved at 101 address is being sent out to the bus. And this data, which is our first number 21, so this is the binary of our first number 21, is being sent to the bus and it is being loaded into the accumulator. And when we pulse it, as we can see, this data has been loaded and stored in the accumulator. So the accumulator now stores our first number, which is 21. No operation will occur at T5. Now here, as we can see, we have already completed our first instruction. Now we will move on to the second instruction. So let us pause the clock again. As we can see, now the program counter has been the program counter had been incremented to 001 at the T2 state of the first instruction, and now it is outputting that incremented value. So we have 001 here, and T1 and T2 states will remain same for all the micro instructions. So no matter what the instruction, the T1 and T2 states will always be the same. So let us pulse the clock. As we can see here, we have the value saved at 001. So at 001, we have the instruction 001110. So this is the instruction at 001. Here, the 001 stands for addition, and the 110 it represents the address at which our second number that is to be added is saved. So the second number that is saved at 110 will be loaded in the B register and then sent to the ALU where the both numbers will be added. Let us pause the clock again. Now we are at T3 state. So as we can see here, the MI and IO bits are active. So the output of the instruction register is sent to the bus and the controller sequencer. Here at the controller sequencer, we are getting the instruction add. So we are getting the opcode 001, which is the opcode for adding. As we can see in the next T state, the RO and BI pins are active. So now the data that is saved in this address, which is the binary of our second digit 1111, the binary of 15, it is being loaded into the B register. As we can see here, this data has been loaded into the B register. And in the next T state, In the next BT state, we can see the AI and EO pins are active. So as you can see, this EO pin is active, and so the ALU has added the two numbers, the output inputs it got from the B register and the accumulator, and it has now added those numbers. Now we'll move on to the next micro instruction. The next instruction, so let us pause the clock. 010, that this is the value of the clock now, the value of the counter. So the first two t states will always be the same, so let us keep pulsating it. Here 0110000, this is the instruction that is stored at the address 010. So here 011 means output, so this is the opcode for the output instruction, and here we don't need any address for this instruction cycle because there is no necessity for it. So here we have 011000, and in the next state here we are getting the output, which is 36. As we can see, the binary of the output has been sent to the BCD converter, which has outputted this decimal value of the output. So our output cycle is complete. Next is the halt cycle. Here, after the halt cycle, our clock has been stopped. So let's check the output at halt. Here the output at halt has become 1, and so our clock has been stopped. As you can see, no matter how much we pulse the clock now, no operation occurs. So the clock has been halted. So this is the complete explanation of the addition operation of our SAP computer. Now let us reset the computer and perform a subtraction. So to perform a subtraction, the only thing we need to change is one single line in the code. So here we just need to change this portion. So this 001, we have to make it 010. So 001 is the opcode for addition, while 010 is the opcode for subtraction. So essentially what this will do is, at the T2 state of the second micro instruction, if you can remember in the previous operation, addition operation, the ALU actually, the EO pin was active, and so the ALU added these two numbers. Now instead of this EO, this SU pin will be active due to our change in the instruction, and hence the numbers will be subtracted. Let us keep the same numbers again. So let us subtract 15 from 21. So we don't need to change anything more. We just need to change this single portion in the opcode. So this single 3-bit number, that's all we need to change. So let us set it at write mode and program mode. So at 001 we will save 010110. 010110. Now let's set it at read mode and run mode. Now let's pulsate the clock again. As you can see, 21 minus 15 equals 6, so we have got the subtracted value. So the operation is the same as when addition is being performed. Now I will demonstrate some of the design modifications and changes that have improved our SAP. So firstly, we have added a BCD converter here at the output unit. So the output value that comes out of the output unit, it is being sent to the BCD converter where it is converted to BCD code. And this BCD code is what is used to show the output in decimal system. So let us go to the child sheet. So this decimal converter, actually BCD converter, this binary to BCD converter essentially uses double algorithm to convert the binary number into BCD code. Next, let us go to the controller sequencer. So instead of 6 T states, we have used 5 T states: T0, T1, T2, T3, T4. So what we did is thus the CE was an instruction, a micro instruction in and of itself, but what we did was we incorporated CE into T3. So this was done because the CE operation itself does not cause any bus contention issues. So it can be placed wherever we want. It does not need to be a micro instruction in and of itself. So we incorporated C with T3, and that enabled us to have just 5 micro instructions instead of 6. So we have just 5 T states now. And another improvement we made is here we have used a demux, a demultiplexer. So from the opcode, this demultiplexer decodes the micro instruction that is to be sent, whether it is add, load accumulator, output, halt, whatever it is, it will be decoded using the demultiplexer. So using a demultiplexer instead of constructing a circuit here has enabled us to use less ICs. It has reduced the number of ICs we needed to use. And so such design modifications have been made in every component. We have made several such modifications to ensure that we need the least number of ICs. So we have tried to make the SAP as efficient as possible. Thank you.